Okay. Last unit we were doing logarithms in base 10. So here we're doing, this is unit 4C. We're starting out with logarithms in other bases other than 10. All right. Before we get into that, we're going to have to review inverses. All right, so if we have f of x is equal to 2x plus 1, we want to say, what is the inverse of that? All right, to find an inverse, you flip the x and the y, and so we're going to have x is equal to 2y plus 1, and then we're just going to solve for y. So with minus 1 divide by 2. So minus 1, x minus 1 is equal to 2y, divide by 2. So we get, we're going to call it g of x. So the original function is f of x. Our inverse now, we're going to label as g of x is equal to x minus 1 divided by 2. So we have our function and our inverse. All right, if you remember the definition of inverses, in order to prove that they're inverses, if we plug in f of g of x, the result should be something specific. So let's actually do that and see what it gives us. So this is a review that we did when we did inverses for a semester. So we take f of x, all right, that's the outside function, and we're going to plug g of x inside f of x. So we take this function, and wherever there's the variable, we're going to write parentheses. So 2 big parentheses plus 1. And instead of x, we're going to plug in the whole g of x function, x minus 1 divided by 2. All right? And then we just go through to solve this. So x minus 1 divided by 2, but it's being multiplied by 2. So when we multiply something by 2 and divide it by 2, the multiply and the divide undo each other. So we multiply and divide by the same thing. So those cancel out. We have x minus 1 plus 1. Well, minus 1 plus 1 is equal to x. All right, so when we plug a function into its inverse, the result should be x. All right, and that should also work for the other half, which is when we take the inverse, just doing it the opposite. So g of f of x should equal x. But let's just go through to practice doing that. So here, the outside function is g of x. So we're starting out here, x minus 1 divided by 2. So x minus 1 divided by 2. And instead of that x, we're going to plug the whole f of x function, which the f of x function was 2x plus 1. 2x plus 1. All right, well, 2x plus 1 minus 1 is just going to be 2x divided by 2. 2 divided by 2 is 1, and so it equals x. All right, so here we're able to prove that f of x and g of x are inverses. All right, and remember another thing about them is that they are symmetrical around or across y equals x. So if we kind of graph that, if we did f of x, 2x plus 1, we'd start at positive 1, and it'd rise to, oh, can't see, rise to, run 1, rise to, run 1. So it kind of would look something like that. Well, x minus 1 divided by 2, if we simplified that to make it look a little bit more, a little friendlier, it'd be 1/2 x minus 1/2. All right, so y equals mx plus b. So our y-intercept is negative 1/2, and it's rising 1, running 2. All right, and like I said, it's symmetrical around y equals x, because if we had y equals x here, the parent linear function, and that's true for all inverses. Every function in its inverse will be reflected across the parent function, parent linear function. All right, so that's just reviewing functions inverses. That's Algebra 1, and the finding the inverse is what we did last semester. All right, so now we're going to add on to that doing logarithms. All right, so if we have f of x is equal to 5 to the power of x, we want to find the inverse. All right, in order to find an inverse, we want to convert, so logs and exponents are inverses. So if we're given an exponent, the way to find the inverse is to convert it into a log statement. We talked last unit about how to do that. Log base b of y is equal to x if y is equal to b to the x. So we're just going to use this to convert here. So if we're given y equals b to the x, we just need to turn it here into this log statement. So it's going to be g of x, which is, function inverse, is equal to log, base 5 of x. 5 of x, 5 of x, and so that became b Okay, looks like I misspoke. So we're going to go back. This is true to make these two things equivalent. All right, so log base b of y is equal to x if y is equal to b to the power of x. All right, but in order for us to find the inverse, the first step we have to do is flip-flop our x and our y. So what we're going to do here is we're going to leave this one the same. All right, so in order to find our inverse, y is still equal to b to the power of x. All right, so the inverse is log base b of x is equal to y. And it makes sense here because we're wanting to write y equals and y equals. So we have f of x and g of x. All right, so the first step is flip-flop our x and our y's. These two statements are equivalent. All right, when we flip-flop our x and our y, now we have the inverse. All right, we've gone from an exponential to a log, or from a log to an exponential. So here, 5 to the power of x, which 5 to the power of x, all right, equals y. It comes over here. We got y equals 5 to the power of x. So bx, bx. All right, so finding the inverse isn't that hard. You're just really transferring it from base exponent, base number. So now we got log of base to that number. Okay. So if we want to test this out, all right, what we have to do, remember, is f of g of x. So f of g of x. This is going to prove that these two things are exponents. It should equal x. So we start off with our outside one, so that's 5 to the power of x. So 5 to the power of x. So in place of x, we're going to plug the whole g of x function. Log base 5 of x. All right, and so what we know that if those are inverses, that it equals x. And we know the same thing if we do g of f of x. That is equal to g of x, which is log base 5 of x. Instead of writing x, I'm writing parentheses, and x is now 5 to the power of x. All right, and so we're going to draw from this kind of what are our general statements. What's going to be true every time, no matter what the base is. All right, 5 to the log base 5 of x is equal to x. So here, 5 to the power of log base 5, those canceled out, and we were just left with x. Log base 5, remember this is a subscript underneath, of 5 to the x, log base 5 of 5 canceled out, and we were just left with x. Alright, so our inverse property of logs kind of boils down to, alright, inverse property of logarithms. B to the log base b of x is equal to x, and log base b of b to the power of x is equal to x. Alright, so this is transferring back and forth between exponent and log. Alright, that if we plug one into the other one, it should equal x, and if we plug the other one into the, back and forth, they should come out to equal x. If you plug one inside the other, whether you're plugging the log into the exponent or you're plugging the exponent into the log, when you work them out, they should come out to equal x. And that's just going back to what is an inverse. Right? If you plug an inverse into the function, the result will be x. It's easier for us to see that when we're back up here doing this, that x minus 1 divided by 2 times 2 plus 1 is equal to x. That the multiply and the divide cancel, and we're left with x minus 1 plus 1. We simplify it out, get x. All right. That's all that's saying, is that if we plug one inside another one, the result will be x. If we plug this one inside the other one, the result will be x. That's all that the inverse property of logarithms is saying. All right, so if we go through and look at some practice problems there, right, it's like 6 to the power of log base 6 of x is equal to x. All right, log base 6, 6 to the power of log base 6, that kind of cancels and we're left with x. Log base 3 of 3 to the power of x, again, is equal to x. The base 3 and the 3 to the power of x, so this is our exponent statement right there. This is our log statement right here. The log and the exponent cancel each other out, and we're just left with that x. All right, 7 to the power of log base 7 of x, all right, is equal to x. Log of 10 to the x is equal to, well, what's the base? It's assumed base 10. So that's equal to x. All right, and then kind of last thing is a natural logarithm is equal to log base e. All right, and it is written as ln. All right, instead of writing log base e, they write just ln. All ln means is log base 2.7. Okay, so it's just changing what the base, instead of being base 10 or being base 3, it's base 2.7. Okay, so e and ln are now inverses. All right, so you're going to be transferring from from e to the natural log. All right, going back and forth between those two. So if we have the log of e to the x, we say what's the inverse? Let's just say f of x is equal to the log of e to the x. All right, that would be g of x is equal to e to the x. All right, and what is this? It's just a different log, and it's just, and rather than writing log base 10, we're going to write ln. So it is kind of an extra thing, but what you're actually doing with that thing is you're not doing anything difficult. So yeah, it looks confusing, but you're not doing anything challenging with it. All right. Instead of writing log base e, we're writing ln. All right. So really, we would say f of x is equal to natural log of x, and then the inverse g of x is equal to e of x. Okay, so that is 23.1. We're going to have to go over to 23.2 and look at that.